Good day, I'm J Wildberger. In today's video, we're going to show how the Algebra of Boole helps us to rethink teaching electrical engineers about circuit analysis. This is a very powerful and effective replacement for the usual Boolean algebra framework, which is currently taught at universities all around the world. So if you're teaching at an electrical engineering department somewhere around the world, you can think about moving to this more effective, much simpler way for students to learn how to do circuit analysis. So the basic idea that we introduced last time was this correspondence between essentially three different things. Between a truth table representing a Boolean function. So here we have inputs A, B, and C, and here's a required function that we want to output depending on the inputs A, B, and C. Okay, it happens to be called f. Values 1, 0, 0, 1, 0, 0, 1, 0 on our sort of standard list of inputs. Now associated to this is this Boole polynumber. It's a polynumber. It's a polynomial expression in A, B, and C, which has the particular property that no exponent is bigger than 1. That's what makes it a Boole polynumber. Okay, and I tried to convince you that there's an exact correspondence between these Boolean functions and these kind of Boole polynumbers. And here's a circuit that captures this Boole polynumber or this Boolean function and takes the inputs A, B, and C and uses some XOR gates and some AND gates, which are the logic gate equivalents of the operations which are appearing here. Here the multiplication here is like an and the addition here is the Algebra of Boole addition, which is represented by an XOR gate. So here we have 1 plus A, that's the effect of this XOR gate on 1 and A, plus B and C, there's B, C, this XOR gate is taking B plus C, so this XOR gate is taking 1 plus A plus B plus C. The cumulative effect of this is output right there. Here's an AND taking C and A, so this is A, C being output there, and when we add this to this with this XOR gate, we're getting this cumulative thing here. This further AND gate is taking the output here, which is AC, and combining it with the B. So this is A, B, C being output here. And when we take the output here and the output here with another XOR gate, we're effectively adding all of this to this. So we can sort of see directly that this circuit is a representation of this Boole polynumber. So today we want to look at some practical problems involving circuit analysis where we exploit the Algebra of Boole to do our computations. So here are the three main logic gates in the Algebra of Boole: the addition, the multiplication, and the OR operation, corresponding to the XOR gate, the AND gate, and the OR gate. And here are the standard symbols for those used in electrical engineering. Okay, so we have inputs A and B, all possibilities 0, 0, 0, 1, 1, 0, 1, 1, and the sum of those inputs is just the mod 2 operation. So just adding these two, mod 2. 0, 1, 1, and crucially 0 here. AB, the product, is just the product mod 2, 0, 0, 0, 1. And here, a little bit more complicated, the usual OR gate, which is like an inclusive OR, differs from the exclusive OR by having a 1 here. Okay, and it's represented in the Algebra of Boole by the expression A plus B plus AB. So basically the sum of these two. Okay, 0 plus 0, 1 plus 0, 1 plus 0, and 0 plus 1. Okay, so it's crucial to remember that the OR gate is represented by A plus B plus AB. Now sometimes it's useful to have a separate operation. We use the circle sum sometimes to represent this OR operation because it's a little bit simpler to write than this. Okay, but that's sort of touching base with the Boolean algebra point of view, but it's very important to understand, okay, that our notation is different from the Boolean algebra point of view. Because for us, it's this addition which is primary, and this one is secondary. Okay? In a Boolean algebra course, it's the other way around. This one is considered primary, and this one is considered secondary. So in traditional electrical engineering courses, usually this operation gets the plus sign, and this one gets the circle plus sign. Okay, so very important that we distinguish our notation here from the usual story. This addition for us is a mod 2 operation, and this circle sum represents this combination in the algebra of Boole. Okay, but primarily we're going to be focusing on the algebra of Boole and working just with the addition mod 2 and the multiplication mod 2, because there everything is just polynomial arithmetic. So it's particularly simple. Now there are three other important gates, which are the negations or inversions of the ones I've just shown you. Okay, so here are A and B, the various possibilities again, and here we're inverting the three main gates. And in the algebra of Boole, we invert by just adding 1. Okay? If you add 1 to 0, you get 1. If you add 1 to 1, you get 0. So adding 1 just flips 0 and 1 around. Okay, so this one, 1 plus A plus B, is the negation of the XOR, and its usual name is XNOR. Represented diagrammatically with an XOR gate with a little circle there representing the negation. Logically, it probably would be better if this was called an N-XOR gate. That would be more consistent with the other names, having the N in front, but tradition is this is called an XNOR gate. Here is the negation of the AND gate, which is a NAND gate. Okay, and it's obtained just by adding 1 to the AB, representing the AND. So 1 plus AB has values 1, 1, 1, 0. Represented by this thing here. It's an AND gate with a negation little circle after it. And then the OR gate negated is the NOR gate. And we just take the OR expression, A plus B plus AB, and we add 1 to it. So this is 1, 0, 0, 0. The OR gate was 0, 1, 1, 1. We're just negating it. All the zeros and ones trade places. We get 1, 0, 0, 0. And the symbol for it is the symbol for the OR gate with an extra little circle in front of it. And I just connect with the more traditional Boolean story. In the Boolean algebra story, we negate by putting bars over things. Okay, so this would be A circle sum B. That's our notation for the OR gate. So the negation would be putting a bar across that. Okay, but in the Boolean algebra, because of the De Morgan laws, this could also be restated as A bar times B bar. Okay, and similarly over here, negating the AND involves a bar over it, and that has an alternative form, again using the De Morgan, as A bar circle sum B bar. Okay, we're definitely going to be thinking of these things as secondary. Okay, we prefer not, in fact, to use the bars, because we want to separate what we're doing from the usual Boolean algebra story. It's different. I'm just sort of connecting things with the usual story. Okay, we're going to try to stick with the algebra of Boole notation, where negation or inversion just amounts to adding 1. So we have the three main gates and their negations, these three here, and those 6 gates altogether are the ones which are the main workhorses to create electronic circuits. So now we can analyze all of those things by using the algebra of Boole. All right, so for our first problem, let's analyze this little circuit involving 2 inputs A and B and an output H, and let's determine the output H in terms of the inputs A, B. We see that there are 3 gates involved, and here's a NAND gate, and here is a NOR gate, and here's an OR gate. And we can refer to the outputs of these two gates as x and y, sort of intermediate steps that help us in evaluating what's going on with the whole picture. So let's look at x, the output of this NAND gate. So it has input A, and the other input is this B, which has been channeled up there. Okay, so this is an A NAND B. That's a kind of a description involving the names of the gates. But we want to replace this with something algebraic. So we have to remember that the NAND gate operation is 1 plus AB. Right? AB, that's the product, that represents and 1 plus that is then the negation of the ands. That's the NAND. So x is 1 plus AB. Well, what about y down here? Well, this is a NOR gate, also with input A coming here and B here. So this is A NOR B. And we remember that NOR is the negation of the OR. The OR is A plus B plus AB. So the NOR is 1 plus A plus B plus AB. Okay, and then H, the final output that we're really interested in, is X or Y, because there's an OR gate here. And we have to remember what the OR gate is with respect to the algebra boole. It's X plus Y plus the product XY. Okay, so now we can put these things together. It's H that we're interested in, so this is going to be what? The X is 1 plus AB, so there's the X. The Y is 1 plus A plus B plus AB, so there's the Y. And we also have to add the X times Y. So here's an X again times Y again. Okay? So we have to evaluate this polynomial in A and B, and eventually we want to output a Boole polynumber. That will be the effect of this circuit on the inputs A and B. Okay, so what do we get? Well, here I've copied what we've already obtained for H, and now we're going to expand this out, just using polynomial algebra like you learned in grade 9 or grade 10. Okay, so 1 plus AB there. And then we copy this, 1 plus A plus B plus AB, fine. And now we have to do this product. Okay, so there's 1 plus AB times all of this. We'll use the distributive law. So let's write it as 1 times all of this. So we just repeat it again. Repeat this one again. And now we have to take AB times all of this. AB times 1, there's AB. What's AB times A? Well, AB times A is like A squared B, but A squared is the same as A in the algebra boole. So this is another AB. Similarly, AB times B is another AB. And AB times AB would be A squared times B squared, but that again is also equal to AB. And now we use the other important simplifying aspect of the algebra boole, that whenever you have 2 of anything, they cancel. It's gone. So 1 plus 1 is 0. In fact, x plus x is 0, no matter what x is. So this term here, being exactly the same as this term here, means that those things are going to combine to give 0. So we have a 1 plus AB from here. These two terms exactly cancel. And this AB and this AB cancel. And this AB and this AB cancel. So the final result is just 1 plus AB, which we recognize is exactly equivalent to a NAND gate. This is the same as A NAND B. So the original circuit that we had is effectively equivalent to this simpler circuit involving a single NAND gate, AB NAND, to create H. Okay, so we've been able to see this simplification algebraically just by doing the simplification, but crucially, the simplification does not require any sort of new kind of complicated Boolean algebra facility. It's just ordinary polynomial algebra together with 2 simplifying properties. The property that 1 plus 1 is always 0, or more generally x plus x is 0, and that x squared is the same as x. In fact, any higher power of x is the same as x. So basically you're allowed to rub off exponents of powers. So this is much simpler, in fact, than grade 9 polynomial algebra. Okay, and it's exactly what's needed to solve all these logic circuit problems. Remarkably. Okay, it's a remarkable thing. People have been doing this for like a century now, and the original insight of Boole has been basically ignored. Well, it's time to undo that and to go back and really apply Boole's original insight. Okay, for our second problem, let's determine the output M of this circuit, which has inputs A, B, and C. So we have 3 inputs now, and we have a NAND gate, there's an OR gate, there's an AND gate, and there's an XOR gate. Okay, so let's look at the outputs of these various gates. Let's call the output of this NAND gate X, the output of this OR gate Y, the output of this AND gate Z. So these are sort of intermediates on the way to figuring out what the total effect is. All right, let's look at X. That's a NAND gate taking inputs A and B. So A, NAND, B, well, that's 1 plus AB. Y is an OR gate. There's an A coming in, there's a B coming in, so this is A or B, which we know is A plus B plus AB. Now Z here is taking the inputs X and Y, and it's an AND gate, so that's X and Y. Well, AND in the algebra of Boole, as in Boolean algebra, is just the product. So it's just X times Y. There's X, 1 plus AB. There's Y, A plus B plus AB. So we need to expand that out. Just polynomial arithmetic with these Boole algebra simplifications. So maybe 1 times all of this is A plus B plus AB, and then AB times all of this will be, well, I've written that out sort of longhand here. So here's an ABA, and then here's an AB squared, and here's an A squared B squared. Okay, now we can simplify this in our heads because we know this is going to be the same as AB. Right? The A squared is the same as A, so this is the same as AB. Similarly, this is AB, and similarly, this is AB. So how many ABs do we have altogether? 1 there, they cancel. 1 there, and 1 there, they cancel. So all of these 4 just disappear, and we just have A plus B. That's what Z is. And finally, M is, there's an XOR gate with inputs Z and our third input C. So it's Z XOR C. In the algebra of Boole, XOR is just our addition. That's our fundamental addition, right? That's the addition mod 2. Okay, Z we've decided is A plus B, so this is just A plus B plus C. That's the answer. That's a simplified form. That's a Boole polynumber because it's a polynomial expression in the inputs with no exponent bigger than 1. It's unique, right? It's unique. That's the beauty of it. There's no other possibility that you can get. You have to get A plus B plus C if you do this correctly. All right, and in our third problem here, we've got a little bit more complicated circuit with 1, 2, 3, 4, 5, 6 gates, and they're all NAND gates. We want to determine the output N here in terms of the inputs A, B, and C. Okay, so you probably know that the NAND gate is a kind of a universal gate. So it turns out that you can make any circuit just involving NAND gates. So if you have a big pile of NAND gates, you can use them to sort of replicate any other circuit. So this is kind of an example of a circuit built just from NAND gates. Okay, so what's actually happening algebraically? Here are the various sort of intermediate outputs, an X output there, a Y output there, a Z output there, a W output there, and a U output there. Okay, let's go through them individually. The X here is the result of a NAND between an A and a B, so it's A NAND B, which is 1 plus AB. The Y here is a NAND between the B and the C, so that's 1 plus BC. The U here is a NAND between, there's an A coming in here and a C coming in, so it's 1 plus AC. Okay, the next one, Z. That's a NAND between X and Y, so it's 1 plus XY. But we know what X is, and we know what Y is, so this is 1 plus AB times 1 plus BC. So we want to expand that out. When we expand this out, we're going to get a 1, and that 1 is going to cancel with the 1 that we already have there, so 1 plus 1 is 0. We'll also get an AB and a BC, and the product of AB with BC, which is ABC. You might think, well, shouldn't it be AB squared C? Well, yes, but the B squared is equal to B. Okay, so we get just ABC as the output there. That's Z. And now here we have a curious situation where this NAND gate is being used with two identical inputs, both of them being Z. So the Z is being routed to here and to here. So this W is Z NAND Z, which is 1 plus Z times Z, or 1 plus Z squared. But Z squared is the same as Z, so this is the same as 1 plus Z. So the effect of this NAND gate taking the input Z in both inputs is effectively just to negate the Z. This is just negating Z. Right? So this is kind of like a NOT operation expressed in terms of a NAND gate. Okay, so now we have W there, and now we can finally get what we're interested in, which is N, which is the NAND between this W and this U. So it's 1 plus WU. Okay, what was W? Well, here's U. Where was U? U is 1 plus AC right there, and the W is 1 plus Z, okay, and Z was this. So it's 1 plus AB plus BC plus ABC. That's now an expression for N, just in terms of the inputs A, B, and C, where now we've removed the intermediate things X, Y, Z, and so on. So now we have to simplify this thing to find out what this circuit is really doing. So I've copied it again here. So there's N, 1 plus this term times this term. So now we're going to expand. So there's a 1 here. Let's take 1 times all of this. So 1 plus AB plus BC plus ABC. And let's also add the product of AC times all of these. So AC times 1 is AC. AC times AB is ABC. Originally A squared BC, but A squared BC is the same as ABC. When we multiply AC by BC, we get another ABC. Actually ABC squared, but the C squared is the same as C. And when we multiply by this, well, we get another ABC, because actually it'd be A squared BC squared, but the exponents can be rubbed off. We just get ABC. Okay, now we look for cancellation. There's a 1 plus 1. They cancel. The AB is there. The BC is there. This ABC cancels with that ABC. This ABC cancels with that ABC, and we still have an AC there. The result, it's AB plus BC plus AC. So we've simplified this. We've got a Boole polynumber as an output. This is a polynomial in the inputs A, B, and C with the Boole polynumber property, namely that all the exponents are at most 1. Now, as a little exercise, you might like to show that, in fact, this output, AB plus BC plus AC, is also the same as AB circle sum BC circle sum AC. So for this particular combination, it doesn't matter whether you use XOR gates or OR gates. The result happens to be the same. Great, so we have a little bit of experience now solving a very important practical problem, which is to take a circuit with lots of gates and to analyze it, to replace it with something algebraic. And we're using the Algebra of Boole to get a Boole polynumber as a result. In our next video, we're going to go further in this direction, and we're going to show how to look at different circuits, seemingly different circuits, and to try to analyze when they're actually effectively the same. That's another important job that an electrical engineer has to learn how to do. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.